This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, I think we better get underway again. So thanks for coming back. Too bad the first time, but it's a terrible time of day, of course, to try to stay awake for 3 hours from 5:15 to 8:15. So I'll make it as entertaining as I can. We just had a few slides to finish off on that first slide pack. Topic 1, Topic 2 doesn't necessarily correspond with week 1, week 2, but so we won't necessarily finish, one topic per week, but we'll come pretty close. And so we just had a few issues to finish off around this last subtopic about signal descriptions and sampling. So we've been talking in the earlier parts about what the limits of human perception mean in terms of what sort of resolutions we need to use to sample at, these issues of different sensitivity to luminance and chrominance we talked about, but we also recognise that there were these legacies, the fact that we have a history and libraries, vast libraries of multimedia material, that means that we are also influenced by them, and in particular things like frame rates from early television and interlacing, which we wouldn't do today and do not do today in a sense. I mean, in the sense that most new television material is captured without interlacing. But the reality is that there's an awful lot of material out there that's stored, back catalogue if you like, that is interlaced, and we need to be aware of that when we define the sorts of parameters that we need to accommodate in a multimedia distribution system. So with that background, the last few slides, we're just bringing that together and talking about some specific numbers. So what sort of numbers, what sort of bandwidths are we talking about? In the case of audio, we recognise that there are these two main categories of service that we need to support. One is based on speech, which has a relatively small bandwidth because our speech, because we don't generate very high frequencies when we speak, but also because of the history of trying to minimise the bandwidth because of the savings in network cost for 100 years of telephony. We only use about 4 kilohertz, which gives limited degradation to the signal, but just we are historically used to it and we accept it for speech. And the other broad category of audio is the high end. So the sort of very high-end audio quality that we can generate today is much higher than that back in, say, the middle of the last century. But nevertheless, the broad parameters are similar in that we want the same bandwidth that matches the capability of the human audio system, about 20 to 20 kilohertz. High quality requirements if possible, and multi-channel for surround sound applications. To put numbers on it, we have a bandwidth for telephony, something less than 4 kilohertz, so we need to sample at about 8 kilohertz. In fact, traditionally digital telephony has used 8 kilohertz sampling and 8-bit resolution, so we multiply those numbers together and we get 64 kilobits per second uncompressed, and indeed that is the bit rate that's been switched around the world since digital telephony was introduced in the sort of 1990s or thereabouts. I suppose it grew slowly over time. Mobile telephony is different because the bandwidth is more precious, the spectrum is more precious, and we compress that 64 kilobits down to something like 6 or 8 kilobits per second, but we'll talk more about that as we progress. The point is that the base signal that we need to deal with is essentially 64 kilobits, 8-bit sampling at 8 kilohertz. Wideband speech has been introduced. It's used in high quality voice services that some telecommunications providers offer, but also it's been used in video conferencing and some radio applications where there's a link between a radio announcer and someone he or she is wanting to interview, say the Bureau of Meteorology. Rather than use the voice, the low bandwidth telephone network to connect the two, because then the guy in the Weather Bureau sounds like he's on the other end of the phone. It's just different. They set up wideband speech links, which have a wider bandwidth. They capture most of the energy of the speech signal instead of just an adequate amount. Sampled at a higher rate, of course, and with more accuracy for each sample. So multiply those things together, you get 224 kilobits per second, which is substantially more. When we go to the high quality audio end, we have this 20 kilohertz upper limit of human hearing, so we need to sample at 40 kilohertz or more, or at more than 40 kilohertz, just standard Nyquist calculation. And we need a multi-channel capability. Anything from stereo, just 2 channels, as this was used in CDs, and typically 5.1 channels for surround sound. So DVDs and these days online video is in surround channel. Surround sound. So I'll get on to what that 5.1 channel actually means, but let's just talk about the sampling rates first. So with CD sampling, we need to sample at least 40 kilohertz, as I said, and what's actually used for CDs is 44.1. It may seem a strange number, but it comes from the history of earliest digital recordings being on television tape recorders. Basically, they needed some device that would record high bit rates, and so they used a video recorder, and for reasons that I won't bother going into unless anyone's interested, the number ended up being 44.1 kilohertz. And if you multiply 44.1 kilohertz by 16 bits per sample by 2 channels, you end up with the rate of about 1.5 megabits per second, which is the rate at which CDs are read and written. DVD, the soundtrack for a DVD video is sampled at also greater than 40 kilohertz. It's actually 48. The reason for that one is essentially, so it's different to that one, to make copying a little bit more difficult. These days it's easy with modern computers anyway, but that was the original motivation. But with more channels, 5 channels for surround sound. Blu-ray soundtrack offers there's much more capacity available with Blu-rays, and so their sampling is up to 192 kilohertz, much higher than, strictly speaking, we need. We could spend an hour debating whether that 192 kilohertz is actually useful. There are some, some in the audio community have a kind of religious approach to belief that they can hear well beyond 20 kilohertz, and therefore they insist that that's essential. But from a technical point of view, having a very high sample rate just makes your filters very easy to construct. So that's one justification for it. But anyway, the sampling can accommodate very high sampling rate up and very high resolution, 24 bits per sample, and up to 8 channels. The surround sound we'll discuss right near the end of the series of lectures where these configurations came from, why there were 5.1 channels of surround sound. It actually came out of the cinema. But this is what 5.1 channels actually means. The 0.1 in particular is a bit odd if you haven't come across it before. So 5 channels comes from a center channel. If this is a video or a TV application or home cinema type of application, you have a center channel near, behind, in front, above or below the TV, just as close as you can, because that's where you want the dialogue to come from. Then there's a left and a right stereo channel, and then these surround channels, left surround, right surround at the rear to give a surround sound feel. Some modern surround sound systems have even more channels than that, but we'll talk about that when we much later on. But we will see in maybe 3 lectures time, something like that, when we're talking about audio coding, that we're not very sensitive to the direction from which very low frequencies come. So, and for that reason, we can just filter them all off and just send them to one speaker. And so you don't need to represent very low frequencies. And by very low, I mean below about 120 Hertz. You don't need to reproduce them in all of these speakers, which makes that speaker construction simpler. You don't need a very big bass speaker. And you only need one channel to feed this low frequency effects loudspeaker, which can be flexibly placed in the room. It doesn't need to be, because we have trouble identifying the direction from which the sound comes, it doesn't really matter where you put the speaker. And because it's only a very small bandwidth, it's just a terminology that's an abbreviation, if you like, to refer to it as 0.1. Not actually 0.1 in terms of the tenth of the bandwidth, but it's just a common terminology. So a 5.1 channel surround sound system looks like this. It's got 5 full bandwidth channels and 1 low frequency ones. And there are variations. There are 7.1, 9.1, there's 7.2 for if you happen to have 2, if you want to have 2 low frequency effects channels and so on. But we'll get to that later on. I just wanted to summarise the numbers with which that we're dealing in the case of high quality audio, and the same with video formats. So the video formats, most common ones are normally based on television formats. We talked about the 2 television systems that we have as legacies from analog times, and different aspect ratios. Old analog television had a 4:3 aspect ratio, meaning, in fact, that's what this slide is, I think. So the ratio of the width to the height is 4:3, and in the last days of analog TV and into digital TV, that moved to 16:9, just because it matches better the view that your eyes have. If you look at the width of your view compared with your height, it's much wider. You have a much wider view, so 16:9 is a bit better matched to that. The numbers in the digital environment have come from the earlier analog ones, and so we have this 50 Hertz and 60 Hertz frame rates, and the numbers 576 and 480 are the number of active lines that actually contain picture material that were included in 625 and 525. So don't worry too much about the details unless you're interested. You know, we can talk about it, but really I don't want to spend too much time on analog parameters. Just to explain where the numbers came from. And then in an attempt to get some sort of commonality between the television systems, the digital definition used the same number, 720 samples across the picture. At least that made it a little bit easier to convert between the North American standard and the European standard. With the move to high definition, many more options were accommodated, and with modern digital processing, it's relatively easy to convert between them. The highest resolution is 1920 by 1080 progressive, so that's why you might see 1080p referred to with regard to DVD players, or Blu-ray players, sorry, or TV sets. If there's a 1080i, then it's an interlaced signal, and that's So in fact, we don't have TV broadcast in 1080p, at least not at the moment. The highest resolution we get with the broadcast is 1080p, just to save bandwidth for the same original reason interlacing was introduced. But there are other resolutions as well. So there's a 1280 by 720 resolution with the name 720p and a number of different frame rates, accommodating film rate, and then the traditional ones around 30 hertz or 60 hertz and 50 hertz. The details are not so important. And now, of course, we are talking about ultra high definition TV or 4K TV, where we have approximately 4 times this resolution again. So twice the vertical resolution, twice the horizontal resolution, so 4 times the number of pixels for each frame. So with that basis, we have a set of numbers with which we can determine how many pixels we have per second to process, and therefore we have got a starting point when we look at compression, and we're going to do that at the start of the next slide pack actually. The last thing I wanted to talk about here though is what's called anamorphic imaging, and that's simply recognizing that the number of samples or the way that we represent an image in a recording medium, for instance, doesn't necessarily have to match its original geometry. So this comes from days of filmmaking. So in film, 35mm film looked like this, and a standard film representation was called 4perf, for perforations. So every film frame had 4 of these perforation holes at the side where the sprockets would go to move the film through. But the problem the cinematographer would have, or the movie director or whoever would have, would be that if he wanted to film widescreen, it wouldn't fit on the film. Either he or she would have to reduce it down to this width, in which case he wouldn't be able to use the full height, or he'd lose some either side. But the solution was to squish it, so to geometrically distort it. Right? And the way that's done is using what's called an anamorphic lens. I've just got an image of one now. Here it doesn't show you very much, except that you can see that it's not circularly symmetric. Right? It's distorted in the horizontal direction differently to the vertical, because it's actually scaling the horizontal direction differently to the vertical, just so it fits on the film. And then, of course, there's the reverse operation when it's projected in the cinema. But that basic technique is, or can be, carried over into the digital world, as I'll show in a second. So this is an example of some actual film where the image looks distorted because it's been squashed in the horizontal direction. But in video, like in electronic video, the same thing can apply. So we might have 720 by 576 samples, but we could do the same thing for a widescreen representation if we wanted. It would just mean that the sampling density in the horizontal direction would be different to the vertical. Right? So there's just no essential reason why they must be the same. And that gets us into this discussion about whether the pixels are considered to be square or non-square. So square pixels just means that the sampling density vertically and horizontally is the same. Yeah. And so you can imagine filling up the picture with squares representing each pixel, and they would indeed be squares in that case. And if the sampling resolution was different, then the pixels would be rectangular. Okay, so I won't go through this, but I'll just mention that I try to put this at the end of each slide pack just as a kind of a checkpoint. So when it comes to revision time, this may be useful to kind of tick off, oh yes, I understand that, I understood that, or not completely clear about that, I might go back and check. So that could be useful to you. Okay, so any questions about that or anything else we talked about last week? I should have asked before. Yeah.
I'm not sure about the curve.
I'm sure others might be interested in that as well. So what we're talking about is these contrast sensitivity curves. So you were unclear about what information we gained from this? Is that, yeah. Okay, so don't worry too much about the fact that this is labelled blue-yellow chrominance and red-green chrominance. It's essentially the same conclusion that we would draw if we used the YCRCB that we talked about last week. We did, didn't we? Yeah. So we talked about breaking the image down into, instead of using red, green, blue, we can use Y, CB and CR. So the luminance value and the chrominance value, or chrominance information. And we looked at this plot, which comes from subjective tests, from putting people in front of displays and seating them different distances away and showing different artificial images and seeing how sensitive they are to seeing detail at different resolutions. And so the key things that we see here, if I just get this thing working, is that we're sensitive to higher frequencies, higher spatial frequencies here for luminance. And this is actually the reason why we want to transform from red, green, blue to a luminance, chrominance type of representation. Because if we're not very sensitive to these higher spatial frequencies here for chrominance, then why don't we just subsample the whole image and represent it at a lower resolution? And this picture I showed you suggests we can do exactly that. Right? When we looked at what happens when we blur the luminance signal, it's very badly distorted, but if we blur, which means low pass filter, the chrominance signals, it still looks pretty good. Yeah. So that's an important bit of information we get from this curve. We also see just how accurately we need to represent the luminance signal if we can distinguish about, say about 500 different levels of intensity at that particular spatial frequency. And that tells us the most accurate that we need to represent our luminance signal. But importantly, it also shows that we need to represent colour information less accurately, right, because of that gap. So we don't need to use as many bits when we are quantizing chrominance information. Okay, and it also suggests that maybe we would quantize different spatial frequencies with different accuracy. Right? Maybe we don't use as many bits to represent low spatial frequencies as we do these spatial frequencies. Right? So there's a series of different bits of information that we can extract from those curves. Does that help? Is that more clear? Okay. So the next topic I wanted to talk about is introducing compression. Why compression? Because for two reasons. From the sort of large numbers we've been talking about, we can see that video in particular, but even audio, generates lots of bits, and so potentially we need to compress them. So it's an important processing stage in delivering multimedia content. But secondly, we'll see later on when we look at things like streaming and the effect of errors that we really need to understand how the signal is represented to see the impact of those things. So if we say what happens when we lose a packet in an IP streaming application, well, what does that packet represent? Is it different if it's compressed data or uncompressed data, for instance. So that's why it's important to understand this topic of compression. And in fact, we'll spend several lectures looking at this topic. But we'll start by introducing the sort of methods and the tools that are used in compression, and look at image compression, and in the next couple of lectures we'll look at video and audio as well. Okay, so let's start with why compress, and this just comes from the numbers that we talked about before, so I'll go through this fairly quickly, but just knowing those numbers that we need to represent audio and video signals means we can just multiply them all together and see how big a file will be generated, or how high a bitrate would be generated if we don't do any compression. When we're talking about video signals though, we need a terminology to describe our subsampling. Remember we talked about, in fact, when I just reviewed that sensitivity curve, we recognised that we might want to sample the colour signal differently to the luminance signal, and we need some sort of terminology to represent that. So, and this is the one that's used in the television industry, and so I think it's worthwhile just making sure that we're familiar with it. So we use three numbers to describe the sampling pattern of colour and luminance. So if this is a series of pixels representing our subsampled signal, every dot or every circle represents luminance samples, so all pixels have luminance samples. And where the luminance samples are filled in, that I'm using that to represent those samples that also have colour. Okay? So in this case, we've got colour, chrominance and luminance for every pixel along this line, but here there's only luminance. That makes sense? And then we've got all colour, all signals, and then just luminance and so on. And this terminology, this JAB terminology, tells us how many chrominance samples there are in the first row, and how many chrominance samples there are in the second row, and how many horizontal pixels are in this repeated block. Now, J is in fact almost always 4. I've never seen another example. So we normally look at a block of 4 pixels wide. So J is always 4. And then we say, within that block, how many pixels have chrominance samples in the first row. So we see here there's 4. And here we say how many chrominance samples are there in the second row. We see that there are none. Okay. So in this terminology, this sampling pattern would be represented as 4, 4, 4, 0. Am I right? 4, 4, 0. Right. So this is a 4, 4, 0 sampling pattern. Does that make sense? It's just a shorthand way of representing this type of sampling. But I've got a couple of practice examples to make sure we're on top of it. So what would that first one be? Remember? 4, 4, 4. 4, 4, 4. Well done. Yeah, that's right. So 4. The first number is almost always 4. It's 4 pixels wide is the block that we're looking at. 4 chrominance samples in the first row. 4 chrominance samples in the second. And when I say chrominance samples, it's both CR and CB. They're almost always. The only exception, I think, is some obscure camcorder format. They're almost always taken at the same spot. So where you see a closed circle there, that means that there's a CR and a CB sample. And it's important to remember that if you're trying to calculate how many bits are representing this sampling pattern. We'll come to that. Okay, so you're right, that's 4, 4, 4. What's the next one? 4, 2, 2. That's right. So we've got 2 chrominance samples in the first row, 2 chrominance samples in the second. And of course, what this represents is subsampling of the chrominance in the horizontal direction, but not in the vertical. We're leaving untouched in the vertical direction. And the last one? 4, 420, that's right. This is this is a very important one. It's very commonly used in television. It's used in JPEG for images because it's reflecting exactly, and I can't easily go back to that diagram, exactly the difference in our sensitivity between chrominance and luminance. So that sensitivity difference is symmetric with with horizontal and vertical, so it's pretty much the same. And so this is subsampling the chrominance by a factor of 2 in the horizontal direction and subsampling by 2 in the vertical direction. Yeah? And saves us a lot of bits. It actually halves the number of sample points we have to represent. In fact, let's just do that brief calculation. Let's say we have 8-bit sampling for each of our sample values at any pixel, right? So we've got, where we've got just luminance, we've got 8 bits, 8 bits, 8 bits, 8 bits, 8 bits, 8 bits. Here we've got 24 bits, right? Because we've got the luminance and the 2 chrominance signals. Here we've got 24 bits, or maybe we count in bytes. So that's 3 bytes, 6, 7, 8, 9, 10, 11, 12. So 12 bytes to represent our 8 pixels. Whereas up in the top pattern there, we have 3 bytes for every location times 8 is 24 bytes. So we've got half the number of samples per second that we need to process and compress. In this case, and hopefully being matched to the human visual system, we can't really notice the difference in most cases. Nevertheless, we don't just, if these other patterns were not used, we would just have to have this one and we wouldn't even need this terminology. What are some, can anyone think of an example of an application that might need this very high sampling resolution? Well, it's still not necessarily, because you still have that, depending on how far you are viewing how far your eyes are when you're viewing the PC monitor, you still have that issue of being less sensitive to chrominance information than luminance.
Satellite.
Why is that? Satellite? Well, if you wanted to preserve enough information that you could keep on zooming in and zooming in, yeah, arguably. Another situation on mobile.
Phone. Our mobile phone.
Well, why would that?
Maybe cinema.
Very high quality application, like the cinema, maybe. Yeah, arguably. You also got, actually, it's interesting to think about that. You've got people seeking at different distances, so maybe you can't assume that they're not going to see that range of frequencies. But also applications that aren't that don't involve human viewers, at least not in the first instance. So if you were gathering video material to go into an editing suite, so before you've produced your final product, you want to keep the highest quality before you're doing your audio editing, or in a television studio if you're doing chroma keying, familiar with chroma keying, so you have the weather presenter standing in front of a blue screen or green screen, and so he or she is pointing at maps and things, but they're not actually there. They're superimposed electronically. And with the chroma key process, wherever the colour in the image is a particular combination of values, meaning this green or blue screen that they're standing in front of, then you electronically substitute another image. So to make sure that substitution is very crisp and you don't have a green or blue halo around the presenter, you want to maintain that high chrominance accurate resolution. Make sense? So the subsampling, something like 4200 subsampling, is very useful when you're distributing a final product for people to view from a DVD or on a screen somewhere. But if your application involves other electronic processing, particularly where it's color sensitive, you might need that high resolution of something like 444. Anyway, we don't want to spend too long on that. Just a note in passing though that when those two numbers are the same, so in this case, when those two are the same, then we find that those numbers also represent the ratios of the sampling frequencies, right? Because this horizontal sampling, the chrominance sampling is half as often in the scanning direction as the luminance, and so some people have misinterpreted what those numbers mean as a result. So just be a little bit careful. You might read something on Wikipedia or something about these numbers representing ratios of sampling frequencies, when in fact they are defined according to this block definition. Okay, so with that background, let's substitute some numbers just to get a feel for how big they are when we don't do any compression. So studio quality TV is sampled at 13.5 megahertz per second, standard definition. When we look at our 422 sampling, just as an example, we have an average of 2 samples per pixel location. I don't want to take too long looking at this, but maybe we'll just look at that in the first instance. So for 422, we've got 3 bytes, 6, 9, 12, 13, 14, 15, 16. So we've got 16 bytes for 8 pixels, so an average of 2 bytes per pixel. That's where that number comes from. That's where that 2 comes from. Multiplied by 8 bits, multiply all the numbers together, and you get 216 megabits per second for a low, a standard definition TV. It's quite a high bit rate. And a 2-hour television program would require, as you see, about 200 gigabytes to store. Now, 200 gigabytes is easily accommodated on today's disk drives, but it's still a significant amount of data to transfer around. You can reduce that bit rate a bit if we just look at the active part of the picture. Remember, there were 576 active lines, so we can do this kind of calculation. Number of pixels horizontally by number of pixels vertically by 25 per second, 25 frames per second, times 2. That's that same factor that comes from the 422 sampling, times 8 bits. Gives us a slightly smaller number, but it's still significant. When we get to HDTV, we do the same sort of thing. We get to some larger numbers, approaching a gigabit per second if it was uncompressed, and approaching a terabyte to store a couple of hours of video. And this is just re-explaining that 422 sampling. Electronic cinema, we'll see a little later where these numbers come from or who defines them, but there are 2 resolutions that are used in digital cinema today. 2048 pixels wide, or 4096 pixels wide, and 2 different frame rates. They use higher resolution per sample, 12 bits instead of 8. And that was a good suggestion about the application of 444, because they're using 3 samples for every pixel, so for all the colour samples. Multiply those numbers together and we end up with, as you see, 7.6 gigabits per second uncompressed. And a couple of hours of a movie takes about 7 terabytes to store. So they're quite large numbers that we would need to deal with if we didn't do any compression. Quickly through the numbers for audio. Voice we already did, generating 64 kilobits per second. Acceptable on the switched landline telephone network, if you like, switched through cables on optical fibres, but too high for the density of mobile phones that we need. CD quality stereo is actually stored uncompressed, so when you multiply those numbers together you get 1.4 megabits per second, and that's exactly what is used for a CD. The DVD audio component, the audio component of a DVD video is that sampling rate we talked about, 48 kilohertz by 16 bits per sample times 6 channels. So we end up with about approaching 5 megabits per second just for the audio. And in fact, the maximum rate that you can read data off a DVD is about 10 megabits per second. So you're losing almost half the bit rate just for the audio if you didn't compress it any further. Now wouldn't worry too much about these classifications because they're not very common here. Has anyone come across DVD audio? Yeah, so that hasn't been a very big commercial success, but people who value high quality music have been enough incentive for some companies to record high quality audio on a DVD disc. So we're just using the disc data capacity, so there's no video. So it's called DVD audio, and it could be in stereo, it could be surround sound. The numbers are here, as you see. If there was no compression, then we're talking about roughly 10 megabits per second just for the audio in those cases. It's quite hard to find those things available for sale. Well, it's quite hard to find DVDs available for sale these days, but the DVD audio is even more rare. Okay, so the bottom line, of course, having multiplied all those numbers or calculated all those numbers, is that without any compression, then we're talking about very large bit rates that we would need to carry over networks. Very large storage capacity would be required on discs or to transfer movies to cinemas and so on. And so that brings us to the need for compression, and we will briefly visit a selection of different tools that are used for compression. I think a useful way to consider breaking down the compression problem is to think of the three major stages that are involved in delivery of a multimedia service. So we have the source, we have the signal that's carried over the network, and we have the receiver. So and we can reduce the bit rate that we need to represent that service according to the information that we might have about any of these. So the first one we're going to look at is the statistical nature of the signal that we are carrying here, and we can exploit the statistics to reduce the bit rate. But also, if we happen to know something about the source of the signal, say if we know it's if we know it's a speech application, then, as we will see later, there are certain characteristics of speech that we can exploit to reduce the number of bits needed to represent this end. Or if we know something about the receiver, we can use that information to reduce the number of bits that we send. So an example of that might be the fact that the human eye is differently sensitive to chrominance and luminance, or that when we talk about audio coding, and we'll get to talk about MP3 for instance, then the way the human ear responds to different frequencies can be exploited to reduce the amount of data that we send. We might find that under certain circumstances our ears might not even hear certain frequencies, so back here we don't even need to send them. That's the principle. So I'll come back to this very, very simple diagram a couple of times as we proceed to just provide some context. But the first thing we're going to do is just consider issues of what we can do about the statistical nature of the signal to reduce the bit rate that we are sending, the number of bits that we're sending. So the principle here is that we have some stuff that we want to communicate. So the stuff could be things like a spectrum, it could be the volume of audio or brightness or colour information, or maybe we're sending different signals. But whatever it is, we need to assign some sort of code words to those things that we wish to communicate, and send symbols to a receiver. So it might be different bit patterns, for instance. Again, a very high level view, but if we know the statistics of the things that we wish to communicate, then we can reduce the number of bits that are needed. And we can achieve that through what are called entropy coding, or variable length coding. So some examples are here: Huffman coding, run length coding, and arithmetic coding that we'll look at here. There are others like Lempel-Ziv, Welch, LZ, or it has many names. There are several variations. Can I just check, are people already familiar with Huffman coding? Anyone not? Okay. Arithmetic coding? No? I thought that one might be new. I have got some slides describing Huffman coding, but I'll go through them fairly quickly if they're just a reminder for you. The basic principle here is that we use our knowledge of the probabilities of occurrence of these quantities we wish to communicate and assign code words appropriately. So if something occurs with low probability, we assign a long code word. Something occurs with high probability, we assign a short code word. Yes, I should just make sure that we're also all on the same page with regard to information theory. So we've probably done some sort of introduction to information theory, I should imagine. Quantitatively measuring information, but so just a reminder of that as well. So if we have some event to be communicated, and we know the probability of it occurring, then the information associated with that event is defined as minus log base 2 of the probability. So essentially, the least likely event to occur provides maximum information. But the important measure is the average information, because we want to convey a whole series of these events or measures of brightness or colour or sound or whatever. And the weighted average of these of the information provides us with this entropy, which is the average information from a series of events. And so the form of this equation shouldn't be a surprise. If this is the information, or minus that log is the information, then the sum of the probability of a certain event times its information will give the average, or the mean. And this is important because it provides a lower limit. Right? Go back to information theory and Claude Shannon, and the classic paper from 1948. It tells us what the lower limit is. So the entropy represents the fewest possible bits to convey our data without any loss of information. So this has nothing to do with transmission errors. It's saying that we cannot represent a given set of data with known probabilities with fewer bits than this entropy. And we know that with a suitable coding scheme, we don't know what it is yet, but we know that it is possible to get arbitrarily close to this entropy limit. And Huffman coding is a simple coding scheme that gets us close to that limit. So you are familiar with Huffman coding, so I'll just go through this example fairly quickly. I think the best way to understand Huffman coding is by example. So my example just has 5 quantities with these probabilities. And the most obvious thing to do if you have 5 quantities to differentiate between might be to say, well, I can't do that I can't differentiate between them with a 2-bit code word. I'd have to go to 3 bits because there are more than 4. So I would take 5 of these possible code words and assign 1 to each of these, and so my average would of course be 3 bits per event. But can we do better? Well, we'll see later that what the entropy calculation is that provides us with a lower limit. Sorry, I thought I had done it there. So Huffman coding orders our events in order of probability, and we construct a tree by adding together the least probable events. So these ones, 0.15 and 0.12 probability, get added together in this tree. Not, of course, we will eventually be able to differentiate between them, but in this tree, the probabilities get added together and the probabilities get reordered. So now this combined probability goes up here, and these are the 2 lowest, least likely events. They get combined together and we reorder, and we keep on going like that until we get the full probability of 1, of course, and then we work backwards down that tree, assigning a 0 and 1 split wherever we had previously combined probabilities. And at that point, we've done the construction, and we can read off the code words that we should use to represent each of our events. So, for instance, the 0, 1, 0 used to represent event D is simply read from the path that we need to take to get to D. We go the 0 path here, the 1 path here, and the 0 path there to get to 0, 1, 0. And the others could be read off similarly.
You have to assign them 0, 1 or 1, 0?
No, it's arbitrary. You can, just as long as you're consistent, of course, at encoder and decoder, but it's arbitrary. Now we can do some calculations and involving the code words that the Huffman coder gives us, and comparing with the entropy. So this table here shows our 5 events, their associated probabilities. These are the Huffman codes that we just created. These are the lengths of the Huffman codes in terms of bits, so 2 bits here, 3 bits there. And so we can find the average code word length. If we send a whole series of these events with this probability, then the average length of code word will be these. So the sum of the probability of that length times, probability of that event times the length used to represent it. That's what these individual ones are. Sum them up and we get 2.27. In the last 2 columns, we do the information theory calculation. So here's the information associated with each event, just minus log base 2 of the probability, and then the entropy is summed up here. And we see that our Huffman code has generated an average word length which is greater than the entropy, as it must be. The entropy represents the lowest limit, but it's also quite close, so we're doing very well. Right? So if that really was a realistic situation, and we had these different events to communicate, and a simple Huffman coder gets us within 1 or 2% of the entropy limit, then we'd say, well, that's pretty good. It's not worth our while trying to construct something more sophisticated. But importantly, we've done much better than this 3 bits per symbol that we would have had to do if we didn't do any variable length coding. Okay, so we've saved about 25% or something. Yeah, we need to remind ourselves, though, when we're doing these sorts of calculations, that the calculations of entropy assume that each event is independent. So we assume that the fact that there's been an event D, does not influence the probability of the next event, whether it could be one of those other events. And that may not necessarily be true. The most obvious way to illustrate that is, suppose we had these were actually the intensities representing pixels in an image, and the fact that one particular pixel has a certain intensity, say it's a quite a bright part of the picture, means that the next one probably is quite bright as well, because images have structure. I'll talk about that a little later. So it is important to remind ourselves that we have this underlying assumption. Just to understand the limits of Huffman coding, though, we'll look at what happens if we change the probabilities a bit. So instead of having events A to E with these probabilities, we have these different events F to J with different set of probabilities. And I'll just repeat the construction of the Huffman coding tree, which is easy. We just keep doing the same thing, combining together the lowest probabilities, which happens in a very neat way in this case. Assigning our zeros and ones wherever there's a combination, we split with 0 and 1, obtain our code words, and then we can repeat the table. And here we see that because of the very high probability of this event, this F event, and the fact that we have to assign it at least one bit, we actually get an average word length which is significantly higher than the entropy. So Huffman coding is not doing quite so well in this situation. Okay, so what could we do about that? One thing we could do is assign code words to a group of symbols. So that fact, as I mentioned, the problem we have there is that we have to assign at least one bit, an integer number of bits to represent each symbol. So we have to effectively round up to the next bit. But if we combine events into groups, then that integer number of bits requirement is spread over multiple symbols, and so we can improve things a little bit. It also means that we can take advantage of inter-symbol dependencies. So if I mentioned that we assume independence when we do our calculation of entropy, then if that might not be the case, we can take advantage of that by looking at groups, because if some groups are more common than others, that will show in the probabilities. So we're taking pairs in this case, in this illustration, and we could assign a code word to each of those, or we could even take a two-dimensional collection of data. Any grouping could be assigned a particular code word. So any question about Huffman coding? No? You knew it beforehand anyway. Okay, so run length coding. So run length coding is another way of exploiting a redundancy that occurs where a particular set of events, I'm trying to speak as generally as possible, but pixel values in this illustration are grouped together. So in this highly artificial example here, we see that we have a series of pixels, all of which are the same colour, this light blue, and then a series of pixels which are all the same colour, which is this black. So rather than encode this image as this is a light blue pixel with these parameters, these colour parameters, and this is a light blue pixel with these colour parameters, and this is a light blue pixel with these colour parameters, then we could instead represent it by a single value and an indication of how many pixels. Right? So value, run length. Then we change to a different value, black, and how long is the black run. This can be used in a variety of applications. It's not so well suited to images directly, or not natural images. Why? Probably pretty obvious. Why wouldn't you use this to represent a photograph that you took with your phone, for instance?
The color is changing, keeps changing.
Yeah, that's right. So even if the colours change only a little bit, the point is that they're not identical. And so So it isn't well suited to natural images. There is a category of image that it's well suited to, though. What would that be? Pardon?
Black and
Yeah, black and white, like a drawing or a document. So, in fact, in the days of fax, no one sends faxes anymore, except lawyers and doctors. I don't know. Fax images were coded using run length techniques or variations on this, because you'd have long sequences of white and then a few black and then long sequences of white. Okay, now the next and the last type of entropy coding I wanted to describe to you is called arithmetic coding. And it's a little bit complicated, but I'm not expecting you to be able to write an arithmetic coder. I just wanted you to understand the principles behind it and why it is as efficient as it is. So the limitations of Huffman coding are that we have to use a whole number of bits to represent a symbol. Even if we group them together, we still have to use a whole number of bits. But the arithmetic coding approach, which was developed by IBM several decades ago and wasn't widely used for a number of years because they held the patents on it and wanted royalty patents for it, but I think they've expired now. But it's a very clever technique, and it allows us to get very close to the entropy limit. And a key feature of this arithmetic coding is that a variable number of samples is converted into a variable length code word. So we haven't just got a variable length code representing each sample or each symbol in a sequence, but we combine them in variable ways. And I'll show you how by way of illustration. The principle of arithmetic coding is that we take a sequence of symbols and we encode it as a rational number between 0 and 1 on a number line, and according to their probabilities. So this is a very general description to try to get the concept across. But the idea is that if we have a sequence of symbols that is relatively likely to occur, we can assign it a longer length on this number line, and a less likely sequence of symbols can be assigned a shorter length on this number line. And as you might expect, you would need more bits to be able to identify a smaller part of the number line. Okay, so we have a sequence of symbols representing a small segment on the number line requires a large number of bits in the case of the low probability, but the high probability one occupies a larger segment of the number line and therefore requires fewer bits to uniquely identify it. Okay, so that's the principle behind it. To illustrate that even more, let's look at another artificial example. So these bit patterns are all made up just to illustrate the point, but suppose the symbol A is a relatively likely or common symbol to occur. So when we map this A by itself onto the number line, we end up with a large segment of the number line, and we have an upper and a lower limit. But then we introduce our next symbol, and so the combination AB will take up less space than the symbol A by itself. Right? So there'll be an AB here, and an AC here, and an AD here. And so this sequence AB can be represented by another set of upper and lower limits. And then similarly, we can keep on adding symbols, taking up a shorter segment of the number line, but representing more data with each addition. Okay. And other sequences of symbols will be assigned other segments on this number line. So I've got an example from a textbook, and I'm not sure if I've already put it on the LMS, but I've copied the relevant pages from the textbook so that you can refer to that if need be. But before I show that, I just want to talk about representing subunity numbers, so numbers less than 1, using binary, because it's not so common. When we learn binary, we we learn about this half of my diagram here. So, of course, you're familiar with the binary representation of integers, where the location of the bit represents 1, 2, 4, 8, 16, and so on. But as long as we know there's a delimiter, then we can do exactly the same thing for fractions. So we can have a bit that represents a half, or a bit represents a quarter, or an eighth, and so on. We can work to the right. So it's probably straightforward to you, but tell me if you have any questions. But this means that, for instance, if we want to represent a fraction like 3/8, we just have to have a bit in the quarter position and a bit in the eighth position, and the other 0. So as long as we know that there's this delimiter somewhere, or we know we're only dealing with fractions less than 1, as we are when we're dealing with probabilities, which is why I'm introducing it here, then we can represent these fractional numbers as binary patterns as well. Is that okay? Yeah. Okay, so let's look at this example of how an encoder will construct will output some bits to inform a decoder what the sequence of symbols is. So we use a very simple example with just 3 possible symbols, A, B and C, with the probabilities that are noted there. And the first thing we do is map our probabilities onto the number line, the 0 to 1 number line. As you see, A represents the bottom half with a half. Sorry, the bottom half of the number line with taking up half of the space because it has the probability of a half. B has the probability of a quarter, so that's how much space it takes on the number line, and C similarly, the top 1 quarter. And that's an arbitrary assignment, but so long as the encoder and decoder both know what they're doing, we have to assign our symbols to this number line. And suppose the input symbol, the first input symbol to come in is A. Then we look at the upper and lower bound of the bit pattern that will eventually be sent. So we're expecting to construct a segment of this number line representing a sequence of symbols. So eventually the upper and lower bound will get closer and closer together, but we want to see what the limits are. So in this instance, the lower bound is going to be 0 for all we know now is that the first symbol is A. So because it's mapped onto that space, 0 to a half, we know that the lower bound is 0 and the upper bound is going to be 1, 0, 0, 0, 0, 1 representing the half. So we can't be sure, we can't unambiguously send any bits to the decoder yet, because the first, we don't know how it'll be mapped onto this range. So we take the next symbol in. So the next symbol in this case is a B in this example. We do the same mapping. We've got this A, B, C mapping across this whole space, but now we're just mapping those A, B, C's onto that segment. Okay, so the first symbol, A, restricted us to the bottom half of this number line, and now we're mapping those same fractions, a quarter, a half, onto that same line. So I've only blown it up here just so we can see it, but we're still talking about the range 0 to a half. Make sense? Yeah. And now we've got this, we know that our symbol sequence, we've got other symbols to add to it, but it starts A, B. So now let's look at what the upper and lower limits are of the bit pattern that will represent the segment eventually. And we see that the lower limit is a quarter, 0, 1, 0, 0, 0, and the upper limit is 3/8, 0, 1, 1, 0, 0, 0, 0. So these bits down here may change later as we add other symbols, but these first ones won't, right? Because the upper and the lower limit both start with the same bit pattern. 0, 1. So the decoder can be told that. So at that point, we can output some bits to the decoder. We can say 0, 1, right? And the decoder can start, the decoder will know that we're talking about this space, and it should be able to figure out that we're talking about AB. Okay, now we just repeat that process again and again, always looking at the upper and the lower limit and whether there's going to be any subsequent change when later symbols are added. In this case, in this example, we go ABA, so we've got, we expand on this range of a half to a quarter, so a quarter to 3/8, quarter to 3/8 here. And now we're mapping another symbol, the third one, A, onto this. So now the length of the line segment is just from a quarter to 5/16. Right? Now, of course, just draw on this in a second. Of course, because of this mapping, what we're really doing is talking about a little segment in here on the original number line. Right? Just keep on zooming in. Okay. So we've defined again or redefined the upper and lower limits, 0, 1, 0 now. We've got another one that won't change no matter what these other bits do. And so the encoder can output this 0 bit to the decoder, and the same thing will continue. Here we haven't got any improvement, right? We still don't know what the fourth bit will be because the upper and lower limits have a different bit in that position, so we can't do anything there. But by the time we've added this fifth symbol, we can see that the upper and lower limits are identical for the first 6 bits, and so we can output some more, I think, right? Another 3. Okay, so that's half the process. Now let's see what's happening at the receiver as it receives these bits. So now remember, when we receive a bit at the decoder, we're not reconstructing this same diagram. All we know is, with every bit we receive, are we talking about the top half or the bottom half of the number line, right? So we've got the same mapping of A, B, C. We know those probabilities. The input bit that we receive is 0, so we know that our upper and lower bound looks something like that. And so we know that we're going to be mapped onto the bottom half of our number line. And so in fact at that early stage we can output A already. We know that whatever the rest of the sequence is, the first symbol must be A. The next bit we receive is a 1, and so now that must be on the upper half of this number line. I repeat that we're not directly reconstructing what was at the receiver, because every bit that we receive simply tells us lower half or upper half. Okay. So as we receive these bits, we can have a better idea of the upper and lower limits of our little line segment. So we know it goes from 0, 1, 0, 0, 0, 0 to 0, 1, 1, 1, 1, 1, 1 until we receive more information. That puts it up in that upper half, but we don't yet know whether we're talking about AB or AC, so we can't output any symbols yet. However, as we receive more bits, another 0 comes along. We know we're in the bottom half of this mapping, and so we can output a B as the second symbol, and so on. I won't bore you by going through every bit that's received, but hopefully you can see the principle that's involved here. Every time we receive a 0 or a 1 bit, we know we're restricting ourselves to the lower or the upper half of the fraction of the line segment that we're talking about. And where that unambiguously defines a symbol, we can output it, and where it doesn't, then we have to wait for more bits. So the end process of all this is that we do achieve this flexible mapping that I talked about earlier, where we have a variable number of symbols represented by a variable number of bits. And by use of this arithmetic coding method, we are able to get very close to that entropy limit. And so where it's warranted to introduce the complexity, because as you might expect, it's a fairly complex bit of software that you have to implement to do the encoding and decoding, it can provide those benefits. If you're left a bit confused, or I went a little bit fast because of all those symbols and bits, then have a look at the pages from the textbook that I'll make available on the LMS and think it through, and if you have any questions, just ask them on the LMS. Is that all right? Okay, so well, it's the end of one of my subtopics. So, and we've been going for about an hour and a quarter. So why don't we have a short break? I'm happy to deal with these breaks as you want. So, nominally, I would have 2 breaks in this time. If you would like to restrict it to 1 and just push through, just to finish a bit earlier, then I'm okay. But it's up to you. Just to think about it while you have a bit of a stretch. I don't want you to push on if it means that you're just going to sleep. I'm just saying that it's the lower limit of this little line segment is 0. It starts at 0, so that's going to be 0, 0, 0. 0 will continue forever, and the highest possible value would be a half, which is 1, and then all zeros follow.
This is I'm confused.
Yep. it's back to the previous slide representing fractions, right? Because there's the first digit. If we assume that we start sending bits, we're not going to have any numbers more than one, so we start sending bits at that point. So the first bit we receive will represent half, and then the next bit will represent a quarter, and so on. So if we just have a half, it'll be 1, 0, 0, 0, 0, 0, 0, 0.
Okay, I know. And another question is, why you don't output the bits like this?
Because the information we have about the upper and lower limit of our line segment is that for the lower bound it starts with a 0, the upper bound it starts with a 1. So we can't unambiguously define it yet. But when we get to here, we see that this line segment always shrinks the further we go. So once the bits that start the lower limit and the upper limit are the same, that won't change. But here they're different, 0, 1. So we've only received the first bit. Maybe I should have grayed those out. Right? So we've only received the first bit. We can't tell whether what the following bits will be. But by the time we get here, upper and lower limits both start 0, 1. So we know that won't change, no matter what other bits we receive later on. So we can output. We can send to them.
And how about this? It's the same. So
The same situation.
Why don't we output 0, 1, 0?
Because we can only output the bits that are common to the that won't change. Because if you compare the upper and lower limits, and the upper limits, they both start 0, 1, 0. So our objective is to tell the receiver what the short line segment address is. Right? Imagine it went on forever, we'd be defining a very tiny line segment, or a point on that line. And so we know we're going to receive other bits, other symbols that will further define these bits after here. But we know that no matter what symbols we receive, the upper and lower limit will start 0, 1, 0. So we can send 0, so we can send 0, 1, 0.
Yeah.
Yeah?
Thank you.
Right. Yeah, we could improve it too. Yeah.
This is just
It's just yeah, that's right. It's just as long as the receiver knows the same or assumes the same thing.
okay. And there's rather than do this is now we know and this is that we those things in the world. And actually this whole thing is the output of the signal, right?
The output from the sender to the receiver.
So actually we only have to know the output at the final stage. Is
Oh,
0,
yeah.
1, 0, 0, 1.
Well, yes, but I mean, but we haven't even finished there. I haven't bothered to talk about the complexity of how we terminate this and maybe start another sequence. But the point is that at that point there's no ambiguity, so you can tell the receiver, you can start outputting bits, right? And you could keep on going.
Yeah. The other one is, I'm a little bit confused because when we talk about compress, we always talk about beats and bands. So this is only about the digital
Sorry, we always talk about that?
beats.
Oh, bits.
Yeah. So wait, the compress is only about the digital things, which is not nothing running with the analog.
No, I mean, if you're compressing in the analog sphere, then you're doing something like filtering, low-pass filtering, so throwing out some information in that sense. But you can't do any sophisticated processing to take account of redundancy between different parts of the signal in the whole case. So in practice, we only really do compression in digital. Good. Okay. Maybe we start again. Yeah, a couple of people still to come back, but I think we better get going. So that was entropy coding, and that wasn't specific to the media case, right? We weren't really talking about image characteristics or speech characteristics, or audio characteristics. It was just some signal that has certain probability characteristics that we can exploit. But the next one in our list here is this possibility of exploiting some signal structure and making some transformations to reduce the amount of information that we need to send. So in this case we're talking about that's the source. So in my earlier super simple diagram here, we're talking about what are the characteristics of the source, what structure exists here that we can exploit to reduce the amount of data we need to send to represent it. So we ask ourselves, what are the characteristics of typical pictures or video, let's use that as an example, which we could exploit to reduce the amount of data necessary to describe them, and how might we exploit them. So to start to think about this issue, I'd ask a kind of a stupid question, which is, do we often see pictures like this? Do you pin up pictures like this to a board at home? Well, hopefully the answer is no, but the important thing is to understand exactly why. I mean, why don't we see pictures like this? Maybe the answer is so obvious you well, signal has been interrupted. It's a good answer. It looks like a random noise, and let me use that to get to the answer I'm after. There's no structure. In images that we typically would pin to our board at home or keep as a screensaver or save in our pictures folder, there is some structure, and what we mean by structure is that there's correlation between nearby pixels. So an image such as this, even though there's a lot of texture, a lot of detail here, a lot of subtle variations in the waves here and the rock structure here, all the pixels around here are a lot more similar to one another than they are to parts over here. So what we expect in a normal picture is that often, in fact for a large proportion of the pixels, there's a lot of similarity between those pixels and their neighbours. That won't always be the case, right? There are these parts here along this sharp edge where the colour changes dramatically and very quickly. But for the normally the majority of pixels, there is this issue of similarity between neighbours. So I'll just talk about that in terms of information theory, and if you're not very strong on information theory, it doesn't matter, it's just another interpretation. But we can interpret these things in terms of information theory. So information theory tells us that we get the maximum average information, so the maximum entropy, when outcomes are equiprobable. Right? So in other words, if we have no idea what to expect, then when we receive some symbol, some message, then we get the maximum information from it. Okay, so, and we can illustrate that with a binary event example. So the binary event is very important because it could mean a series of zeros and ones. So if we're transmitting zeros and ones, then that calculation of entropy earlier with probability of p for 0 and 1 minus p for 1 turns into this expression. So we've got an expression for h in terms of one variable p, and if we plot that, then we get this result. And so this shows us that if the probability of, say, a 0 is very small, close to 0, then the average information conveyed per bit is very small, it is near 0. And we get maximum information when the probabilities are equal. So, in other words, given that I've received a whole sequence of zeros and ones, and given that I have all the information about what they represent, if that helps me to guess what the next bit will be, so the probability is less than 0.5 or higher than 0.5, then I'm not sending as much information as I could. Ideally, to maximise the information I send with every bit, I would rearrange my data in some way such that all events would be equiprobable. And that same principle applies to pixels, to images, to audio samples, whatever. If I can guess what, if I can make a good guess about what the next value is going to be, brightness or colour or whatever for a pixel, then I haven't conveyed as much information as I could with my available bits. So, to try to make more use of available bits, or to get more information per bit, our objective is actually to decorrelate the information we send. So we can transform our pixel data, I'll stick with pixel data as the example, so that ideally all possible outcomes are equally likely. And if we achieve that, then we maximise the information content for every bit we send. Or, looked at a different way, use the minimum number of bits to represent our image. So there are different ways, several different ways that we can transform our data to exploit the correlation that's present. And we'll look at these three. So predictive coding is the first one, and the idea of predictive coding is simply that. Let's go back to that image. Instead of encoding, let's see, say we're scanning across the pixels that represent the sky in the top part of that picture. Now the crude representation, or sorry, the uncompressed representation of that image, I think 444 sampling, is that we have 3 bytes representing every pixel, and we redefine for every pixel the values for red, green and blue, or for luminance and chrominance, again every time, right? But clearly we have a lot of similarity. So instead of sending that data about the particular blue colour of the sky for every pixel, we could say, well, the first pixel has this intensity and colour, and the next one is different by this much. We just send the differences, right? Which effectively is saying we're predicting the second pixel based on the information we have from the first. So we send the information describing pixel 1 to the receiver. The receiver can predict what the second pixel will be. The encoder does the same prediction, and we just exchange the differences. Okay, so the principle is very simple. Principle of predictive coding. So here we have a series of sample values, just a one-dimensional example, being input to our encoder. And the idea of predictive coding is that the encoder makes some prediction. It really doesn't matter what the algorithm is, but ideally, of course, it makes a good prediction of what the next value is. So it might simply be using the last sample value. So it makes a prediction of what the incoming signal value is. We do a comparison. We find the difference, the little red arrow there. By the time, and at the corresponding time at the decoder has made the same prediction. So it has to be making the same algorithm. So what the, sorry, just go back. So the encoder just has to send to the decoder that little difference signal. That's the idea behind it. And so since the decoder had the prediction, it can add that prediction error and reconstruct the original sample value. And then we go on to the next one. So the encoder makes a prediction, compares with the incoming signal. This time the difference is a negative value. The decoder is making the same prediction, receives that prediction error information and reconstructs the output value, and so on. And continues. We're still sending one number per sample though, so why is this a good thing to do?
If we can predict very correctly, so we will send less differences.
Yes. Well, if our prediction is good, then it's really the range of values that we expect that we can benefit from here, because those input values might be, well, in fact, my next slide illustrates this, sorry. So here's an example original image, and this is the histogram. So we've got values from 0 to 255, just the black and white component, of course. But if we think about coding the differences, then we can look at a slice out of this picture. There's one row, or a representation of one row up there, in which we plot the one-dimensional value. And for much of the picture, of course, we will have relatively small changes for the reasons we talked about earlier. There's this correlation structure in our image, so many pixels will be very similar to their neighbours. And so we'll have this small prediction errors, this small change as we just predict what the next pixel value is based on the previous one, for instance. Every now and again we'll come to an edge, a sharp edge in our image. Our prediction will not be good and we'll have a large delta, but for most pixels we hopefully will find that the values are relatively small. And and I think this is what you were getting at, you didn't put it in these terms, the values that we get for all these prediction errors are going to be highly concentrated near zero. The numbers here, the scale is very small, you might not be able to read it, but you'll see it in the PDF. We're talking about values between -50 and +50 here that encompass virtually every value. And it's very highly peaked near zero because, of course, most of the time our prediction is good and we just send a very small correction. Interestingly though, well, what's the... no, I've already essentially explained it. The range of possible values has actually expanded. Here we have 0 to 255 now, so that's the range of possible pixel values, but because we could be predicting let's take an example. We could be making a prediction based on a white pixel here. We might be predicting that the next one will be white, and in fact it's black. Right? So we could get a very large, which way around is it? We could be getting a large negative error way over here, at near -255. And the reverse could also be true. So maybe we are predicting black over on this side of the hat here, and it turns out to be white. So because of that sharp border, so then we could have an error of +255. So these are very unlikely events, but they could happen. And so the range of possible values is actually expanded from -255 to +255. However, because they're so rare, that we might just quantize and only allow a small number of values near 0 to be transmitted, and ignore those ones. But, but I should have related this back to what we were talking about earlier. And that is that the probability characteristics of this are well suited to Huffman coding or entropy coding. Right? We've got these very high probabilities for some values to which we could assign short code words, and lower probabilities for these other values to which we could assign longer code words. And so we could exploit those signal characteristics. Okay, how do we generate this prediction though? I've just said, maybe we can just use the previous value, or we just come up with a prediction. Doesn't matter very much, but let's think about what we want to do. We've got the series of signal values xi labelled there coming into the encoder, and we're making a prediction for each new one, and we're sending the difference to the decoder. Hopefully there are no transmission errors, so the decoder receives that difference signal without any errors, and the decoder has to make the same prediction. Okay. So we could say, the obvious thing to ask is, could we just use the last input value as a predictor for the next input value? And that would be fine. We know the encoder and decoder need to make the same prediction, and if the decoder reconstructed exactly what was coming in on the input, then we wouldn't have a problem. But before sending it, what we'll actually do is, as I was suggesting with the previous slide, we'll quantize that difference signal here. Right, so what we send to this decoder, and therefore what the decoder reconstructs here, will be a little bit different to what's here.
The
Yeah?
encoder predict based on the input, right? But what about the decoder?
Well, exactly, that's right. See, the decoder doesn't have that input available, of course,
Yes.
because of this quantized data.
How does the decoder predict based on what?
Well, the decoder has to predict based on what it receives as quantized data.
Changes based on the difference between the predictable bits and the because the encoder send only the changes.
Yeah.
Difference.
Yeah.
So how come the decoder predict based on the
Well, the decoder is using those predictors, that prediction error, to reconstruct. Just hold on to your question for a little while. I think I'll answer it, but if not, tell me. Without addressing that immediately, the encoder has to get around this problem, the problem of the decoder basing its prediction on different information. The encoder really has to predict its value here based not on the incoming signal but on the quantized value it sends to the decoder. So they have to be able to make the same prediction. So we put the quantizer in there, and we don't base the prediction on the input signal, but rather we have to base the prediction on what is being sent to the decoder in some sense. So naively we might say, well, maybe this will work. Will this work if we take the difference, quantize it, and then use that to predict the next value? You can see I'm laying a trap here for there's something wrong, but what's wrong? The problem is that we're taking a different signal here. We're quantizing it, but we've got a different signal here. So we've got those very small numbers centered around 0. 0, plus or minus 1, plus or minus 2, So we can't use those directly just to predict here because we've got these big numbers, the original numbers. So, so we have to do something a little bit different, and I think the easiest way to understand it is to consider what has to happen at the decoder. We need to emulate at the encoder what the decoder is doing, so let's think about what the decoder is doing. And the decoder is doing something pretty simple. It's just using the last value it reconstructed, the yi output, and the delay, by the way, is just a single sample delay, so we use yi to predict yi plus 1. Yeah? So the decoder is using the last output value yi to predict the new one, and then it receives the quantized difference signal to generate the next yi plus 1, which it then uses to predict the new one. So if we think about what has to be done at the encoder, we just need to reproduce exactly this. Okay? So at the encoding end, we know we need to generate some prediction. We take the difference from the input signal and we're going to quantize and send that off to the decoder. But that is just that signal. Okay? And this one is this one. Yeah? So if we take our quantized difference signals here, put them into this little construction here, and take the prediction from this point and connect it to there, then we'll be doing the same thing as the decoder. So if we just take that decoder, we build a little decoder inside our encoder, and just to help with the visualization, I'll just rotate that, so just it shows that the quantized different signals are going into here. Then we've just got to take that and connect it to there, and which is shown there, and that's what we need to do. Okay, so we have again, this delay is just a one sample delay. So we've got a prediction. We take the difference from the next input signal, it gets quantized, then the quantized version gets added to the prediction, and that is then delayed by one sample and then used to predict the next one. Is it okay? Let me just go through that one more time. So we have a prediction for x of I, so let's call this x hat of I if you like. We've got a prediction error. We're going to quantize it, and it's the quantized version that we will use to generate the next prediction of xi plus 1, because that's the only thing that the decoder is going to be able to do. So we take the quantized version, add it to our prediction, store it there, and it stays there until our clock goes over to the next sample, and then we're using that one to predict xi plus 1. Yeah? If you're still unsure, maybe you need to think about it at home. And if it helps, you could just think of this as a series of numbers, you know, make them up, 10, 11, 12, 9, 13, 11, 10, whatever. And think about what happens around this loop and the numbers that go here and what gets added to there and then gets translated to become the predictor for the next sample. What was I going to say? Oh yes, one thing you might be wondering about is how you start this off, right? If you're always trying to make a prediction. But in fact, it will work even if you just say, let's predict x0 with the value 0. Right? If we start off with this being empty, we just say this is 0, as long as the decoder is doing the same, it's okay, because we'll have 0 here. So this is 0, this is x of 0, which might have some value. Let's use a pixel value of 150. So the error is 150. It gets quantized to something, doesn't matter, 120. it then gets added to our prediction of 0, so this is 120, and that's used to predict the next value, and the decoder will do exactly the same thing. Okay, so that's predictive coding, and now how important is predictive coding? Predictive coding is not used to, it was used in very early image and video coding systems, being applied to pixel values in the way that I've kind of illustrated it here. But there are more efficient ways that we'll explore in a moment. But to represent the pixel values, but predictive coding is used very widely to encode all sorts of other data, and we'll keep on coming back to it. So it isn't used to encode pixel values directly, but it is used to represent other quantities, and it'll become very important when we talk about video coding. Anyone want to guess why? Just the answer to that. Why would predictive coding be very useful for video coding?
Between the two frames there is no such a difference.
Yeah, exactly, because we're now talking about another dimension where we've got slices in time, and if the frame doesn't change very much from one time slice to the next, then we can use the last frame to predict the current frame. But we'll come back to that. Sorry, you had a question.
Does the prediction process start from the second step? Because the very first one, you got nothing to predict.
Well, it starts from the first sample,
That's pretty the first one.
but the prediction is something like I
Like
illustrated
zero
the
and-
example of 0, or perhaps if we're encoding pixel data 0 to 100, 0 to 255, maybe we make our first prediction 128, just to be twice. So the first prediction error will be a large one, but really it doesn't matter very much in terms of the total number of bits, because we've got a few megapixels in an image, so it doesn't really matter if the first prediction is not very accurate.
Okay, so the first prediction can be
Every poor.
can be anything.
Yeah,
And
pretty much. Okay, so I had three of these techniques to try to decorrelate our data. The first one was predictive coding, so you can see why this is decorrelated. Actually, I should have addressed that directly. If we go back to this representation, think about the neighbouring pixels here. This part of the image probably has pixels from this part of the histogram, and so these the pixel values are highly correlated. If you know what one of these pixel values is, the others are going to be quite similar. But if we are sending prediction errors here, then the fact that one of these these prediction errors might be, say, -2, doesn't tell us very much about the next one, right? Maybe it's an intensity that is changing gradually like this. Maybe it's gradually increasing in brightness, and so there will be consecutive +2, +2, +3 sort of errors. But knowing one prediction error to represent one pixel will not tell you very much about the next one. Yeah? In other words, we have in fact decorrelated the data. It's not so easy to predict one value from another one. And so it's another way of interpreting what we're doing. We can instead just think of these values as being highly concentrated in a small number, which has a highly peaked probability distribution, which we can exploit with an entropy coder, but we can also think of it as being as having decorrelated the signal. So another way to transform our data and decorrelate it in some way is to look at a frequency domain approach. I'll explain frequencies in the spatial, well, we've talked about spatial domain frequencies somewhat before when we were talking about those how close together objects are and those sensitivity diagrams. But the principle of pyramid or subband coding is, they're very similar, is to break down the image or the sound, it's actually more commonly used these days in audio, into different frequency bands. And then we can encode each of those frequency bands according to the methods or the characteristics that are best suited to them. So, for instance, we might find that if this is a relatively smoothly changing picture, we've said that there's a lot of structure, there's a lot of commonality between the neighbouring pixels often, not so much in this part of the picture, sorry, but in this part of the picture certainly, then there might not be very much energy in the high frequency band there. And so we might be able to encode that frequency channel differently to these other lower frequency ones which might contain more energy and also to which the human visual system might be a bit more sensitive. Don't want to talk very much about this this approach, but I just wanted to introduce it though because we'll come back and see it a little bit later. The difference between the two approaches, this subband or pyramid, is simply really in the way they're implemented. So the subband coder is the most obvious implementation on the right, where we have a bandpass filter with upper and lower frequencies and a particular coder, then another separate filter defining another band and followed by a suitable coder and so on, which looks a lot simpler than the method on the left, except that this has a very regular structure which may make it easier to actually implement in hardware, where we just have a low pass filter, we code the output of the low pass filter, then decode it and subtract it from the input, so we've got a different signal, and then we repeat exactly the same operation, exactly the same operation. So it's just, and because it's hierarchical, it's called a pyramid coder, but it's effectively doing the same sort of thing. The output in the case of an image looks something like this. So we've got frequencies in both dimensions, and I'll get to that in just the next slide. But we've got the high frequency, the very high detail here in horizontal and vertical directions. And you see that that's largely grey, so there's not a lot of content there. So we could, for instance, throw away that, just zero it, accepting some small degradation to the picture. But we see here some high frequency content in the horizontal direction, but low frequency content in the vertical. I think I've got that right. And the reverse here, and you can see that there's still some content here. But the point is, by breaking them down into different frequency bands, we can code each one according to the amount of structure that's in each of them. Okay, spatial frequencies and two-dimensional spatial frequencies. We've talked about the spatial frequency because we had that diagram, the one where the spatial frequency was increasing from left to right. So you understand what that means. When we represent two-dimensional spatial frequencies, well, when we're talking about spatial frequencies in images, we're talking about two-dimensional spatial frequencies. So they need to be represented on two dimensions, and just by convention, normally the lower frequencies are placed in the top left-hand corner, and the higher frequencies, high horizontal frequencies are represented to the right, and high vertical frequencies to the bottom. But it is arbitrary, it's just by convention. There's absolutely no reason why we couldn't put the origin down here, but this is the way that it's typically represented. So a high horizontal frequency is shown is illustrated by that example in the top right. You see here that nothing is changing vertically. Right? So if nothing is changing vertically, we have 0 vertical frequency. Yeah? But we have a lot of changes in the horizontal direction. So we have a high horizontal frequency, 0 vertical frequency. So you can probably guess what this is going to look like. Down in the bottom left-hand corner, we're going to have 0 horizontal frequency, but high vertical frequency. So our example will look something like this. And where we have both changing in the bottom right corner, we have that sort of pattern. Right, we've got high horizontal and vertical frequency. What do you think the top left-hand corner is going to look like?
Small picture. I'm very detailed. I'm
0 frequency.
one block.
Pardon?
Plain picture.
Uniform. Yeah, that's right. So it's just grey. Right? We have 0 frequency in both horizontal and vertical directions, so it's just a constant uniform intensity. In terms of the terminology that's used when describing these frequencies, that 0, 0 term is sometimes called the DC term. So signal processing people get frustrated and say, why are we talking about DC? Where's the direct current? But it's just because electrical engineers have referred to a constant value as being DC for many years, and so the label has stuck. So we sometimes refer to that 0, 0 frequency as being DC and everything else as being AC coefficients. Okay. So in the case of, if we can break down our image into a frequency-based approach, then what we might do to encode it is something like this. So we could take our image, we could transform it into some frequency-based representation, and then encode the result. And the reason why we might want to do that is that we've said that large structural components of our image can be represented by low frequencies, and the fine detail can be represented by high frequencies. And to perform a transform of this type, we can separate those out and encode them appropriately. Just a note again about convention and visualizing these things. So to visualize 2D transforms, we often represent them as intensity arrays, as I have there. So that's just showing the magnitude, not the, if there's a, if it was a Fourier transform, you'd have real and imaginary parts, or magnitude and phase, but we're just seeing the magnitude here. And so black means magnitude near 0, and white means a large magnitude. And you'll see that we're also, by following that convention about low frequencies being in the top left-hand corner, you can see that most of the energy has been, in the transform domain, has been pushed up into this top left-hand corner. And most of this is sort of near black, so very small magnitude. And in that transform domain, we'll see that the low frequencies represent the large features, and the high frequencies represent the fine details. So what are the transforms that are suited to compression? There is an optimum transform that mathematically, theoretically maximizes the decorrelation process. It's called the Cahunin-Loew transform, but it's not actually used in practice because the transform itself is dependent on the image statistics. So what do I mean by that? Well, when you perform a Fourier transform, you know that you're using cos or sine terms as the multipliers, or or a complex exponential. But the actual transform itself, in this case, is dependent on the image itself. So it's very complex to generate, and you've got to communicate the transform coefficients to the receiver, as well as transforming the image. You have to tell the receiver what the basis functions are that you're using. So there are other suboptimal transforms that are used, and the most important one is this discrete cosine transform. And the reason that's most important is that if we make some simplifying assumptions about our image, that there is increasingly strong correlation between adjacent pixels, then it turns out that this becomes a very close approximation to this optimal one. So don't worry too much about this KLT transform. It's really the discrete cosine transform and some approximations to it, in particular integer approximations to it, that are most important. So the discrete cosine transform looks like this. It's very similar to the discrete Fourier transform, except that it uses cosines instead of complex exponentials. And as a result, all calculations are real, so there's no complex arithmetic. The inverse transform has essentially the same form as the forward transform. And like the FFT, the fast Fourier transform, there are fast algorithms that exist to implement the one-dimensional transform. But now with images, we're talking about two dimensions. So our two-dimensional transform looks a little bit more complicated. It looks a bit scary, but in fact there's nothing very complicated about it. It's just that we see that we have a transform in both dimensions. So we have an x coefficient here and a y coefficient here for the two different cos terms. Otherwise, it would be it has exactly the same form as this one. Now I mentioned that it involves only real calculations. It is for most images, it's a good approximation to this theoretical best one. It has good energy compaction characteristics. What do I mean by that? It's a different way of saying decorrelation. So the fact that if we transform an image, then we find this sort of appearance where most of the energy is compacted into a small number of coefficients. It means that we have effectively decorrelated it. You can't we find that we can't guess some coefficients by knowing others, essentially. In terms of performing the calculation of this two-dimensional DCT, that looks a little bit scary, right? Because we have, for every output value here, on the left-hand side, the C U of V, we have a n by n weighted sum of every input value in our array. So there, it looks like n to the fourth operations. Right? We've got n squared for every value of u and every value of v. There are n by n of them. But the DCT, like the FFT actually, has this property of separability, which makes things a little bit easier, and I'll show you what that means. This is just a repeat of that construction of the forward two-dimensional DCT. But we can see that, for instance, that cos function here, the first one, is independent of y. So we can actually take it outside that second sum. Okay? And so we can reconstruct it looking like that. And what that means is that in terms of calculation, we can do a one-dimensional transform on all the columns. So we can do a one-dimensional transform in all in this direction. And once we've got that result, we do a one-dimensional transform on the rows. Okay, so So it doesn't become an n to the fourth calculation. It actually comes down to n cubed, or proportional to n cubed, and there are fast algorithms that make it a bit lower, a bit better. So, but the main point is that we don't have to do that huge calculation for every output value. So we apply the one-dimensional transform to all the columns, then all the rows. Well, we could do the reverse. I'm sure you can see how you could manipulate the equation to do that, and that saves a lot of calculations. So I've just pushed on until it's now 7:30. Do you want to just go for another 15-20 minutes and then stop, or do you want another break? Keep going? Yeah? Okay. I'll at least finish this transform domain material, and then we'll decide. Okay, so we might be tempted to think, if I go back to this diagram, that we just take this, when we want to do this transform, this DCT we've decided to use because of its nice characteristics, that we take this entire array representing this image and we transform it, and we have one big array in the transform domain. But in fact, we don't. The way we process this is that we actually split the picture up into blocks. So we take our image, we segment it up into lots of normally square blocks, and perform a DCT on each of these to compress or to decorrelate the data within this block. There are a few reasons for that. One is that we save some computational complexity. There are some numbers here that just give a show that there is an advantage. I'm not going to go through it, but there is an advantage with the example figures here. It's about a factor of 4. It's not huge, but it's worth doing. So there is a saving in computational complexity, but there also is an issue of local adaptivity, which I'll illustrate in the next slide. And essentially, if we have recognized that the correlation or the structure or the similarity between pixels will extend over many pixels, over several pixels, but it won't extend over the entire image. So it turns out there's no big advantage in transforming the whole image. But I can illustrate this local adaptivity thing by with an example image. So we'll start by looking at the DCT of a whole image. So I've just extracted the Y component just so that we've only got one array to look at. Otherwise, we have to have a look at 3 at the same time. That's all a bit confusing. So when we're actually coding pictures, we do the transform on each of the 3 components. But here we'll just look at one, the Y component. Okay. So if we take that whole array and do one big DCT, then we end up with this array. We see that we can see that there's some concentration of the energy up in this top left-hand corner. There's more white here, indicating higher magnitude, than down here where the black indicates there's fairly small magnitude. But the next slide, an animation, shows what happens when we split the picture up into smaller and smaller DCT blocks. So this is our original picture, of course. This is just this is a repeat of what I just showed, a single DCT. But let's look at what happens when we segment the picture up into quarters and then transform each of them separately. Right, so we have 4 arrays, which look slightly different, but let's keep on subdividing. So 160 by 120 blocks, and so on, smaller and smaller. And you'll see that there's quite a bit of variety in the appearance of those different blocks because they come from different parts of the picture. And in particular, the statistical characteristics of the sky up there are very different to, say, around this boat. So, if we use, if we apply the transforms on subblocks of the pictures, we can see that we might want to encode the output coefficients in a different way depending on these local characteristics. That's what I was saying about local adaptivity. Okay, we might want to keep more coefficients and keep them more accurately around here than up the top, where the picture is so smooth that there are only low frequency components present, and so we might might throw away high frequency coefficients up in that part of the picture. Does that make sense? Yeah. I can keep on going down. We've got 8x8 blocks here, and even 4x4 blocks here. And you can see that we're getting closer and closer to actually seeing the original picture. But the important thing to observe is how different the characteristics are of the DCT, and how they change with the local characteristics. So the statistics of this image vary a lot across the whole of the array, and so the DCT statistics vary as well. So just an example numerical illustration of the DCT. Suppose this is a block of 8x8 pixels, and is representing roughly mid-range intensity in a 0 to 255 scale. And when we transform to the DCT, you'll see that we have a very large figure up here, which represents the zero frequency term. So this is essentially, it's proportional to, it's a scale version of the average here, average across all those numbers. And then we have some sort of larger value coefficients here, and then we end up with a lot that are quite small. And to anticipate where we're going, if those coefficients are quite small, then we can probably throw them out just to zero. But we'll look at that in more detail later on. So the inverse DCT, of course, goes back the other way there. I wanted to give an additional way of looking at the DCT, which is to think of it in terms of basis functions. So when you were first introduced to the Fourier transform, you were probably shown a diagram something like this. And you were told that if you take a square wave, you can break it down into component basis functions. That is a sine wave that looks like this, and then one that's 3 times the frequency, I think. Is that right? Which is the grey one, and then the black, so much of the black one, which is 5 times the frequency. And then when you add them all together, then you're getting closer and closer to the original square wave, right? You were introduced to the Fourier transform, something like that. And the DCT is exactly the same in principle, that it's made up of these basis functions. And so what we're doing when we transform an image or a block of image data into the transform domain is extracting what the coefficients are that you need to multiply by the various basis functions to get back to the original. Except the basis functions for a DCT look like this. A two-dimensional DCT look like this. Right, so instead of a low frequency sine wave that has a certain coefficient associated with it to match the square wave that we're trying to get to, and then another coefficient for this this sine wave, or cosine wave, we have basis functions here that are multiplied by the coefficients in the 8x8 array to get back to the original. Yeah? Does that make sense? Yeah? Okay. So Another way of, so to just make sure that we understand exactly what's happening here, here's an example. And this, on the right hand side, we're just seeing there are multiple ways in which we can visualize these two-dimensional arrays. Here we've got pixel values in terms of numbers, here we've got a 3D plot of those numbers, or we've got an intensity array. And in this case, we've got in the DCT domain, so in the transform domain, we have a simply got one coefficient in the top left-hand corner. The top left-hand corner represents zero frequency, or constant intensity. Yeah, DC, that's right, DC term. So when we do the inverse transform into the pixel domain, we end up with a uniform array here, which is reflected here and here. But in terms of basis functions, sorry, just 3 ways to represent the pixel value. In terms of basis functions, we're saying what this represents is a 700 times the basis function in the top left-hand corner, so 700 times that one there from this array, 700 times that one, and 0 times all the others. And we add all those together, and we get this output. If we put an AC coefficient in there as well, let's add a non-zero frequency value at 100 there, then now we've got an AC term, so there's we don't just have an average, a constant pixel output, and now we're defining a low frequency horizontal frequency component. So now we've got some variation left to right in the horizontal direction, but no variation top to bottom, because that has 0 vertical frequency. Yeah. So in the so we see that we now have this variation of intensity combining those two coefficients. And so in terms of the basis function representation, we're saying 700 times that basis function plus 100 times that basis function added together and scaled, and we end up with that. Is that all making sense? If I move that coefficient one more space, it represents a higher frequency in the horizontal direction. So the variation in intensity is not just gradually decreasing over that array size, but it actually has a bit of a cosine type shape there. And with the basis function representation, it's 700 times the average value plus 100 times the next basis function in the set. Yeah, I don't want to waste your time going through too many examples. So, in other words, if we end up with a transform, we take a certain 8x8 array of pixels and transform it into to obtain DCT coefficients, then what that's saying is that array of pixels can be obtained by a combination of 1203 times that basis function plus 123 times that basis function plus. Okay. Just like the sum of sinusoids. Okay. I reckon we're probably done for today. Are you done for today? Let's finish there, and we'll continue next week. I should have mentioned about the little tasks I asked you to do. I'm not sure that everyone has done that exercise of calculating the optimum viewing distance for your phone, but I appreciate that you do it if you haven't, because just doing the calculation raises these little issues about which dimension of the phone am I using, and for instance the question that was raised, am I using the whole phone height or just the screen height? These sorts of things just come up, and you won't understand them if you don't just go through that exercise. So I think it's a good thing to do. I was still receiving some suggestions of what the important areas of multimedia were this afternoon, so I haven't compiled them together, but before our next lecture I'll do that. And so that is intended to be just to trigger some thoughts about what your individual projects will be. It's not, you're not locked into any of those ideas, but we'll talk more about that next week. One thing though about those projects is, and it's illustrated by the fact that a few people have mentioned 5G and multimedia to me as possible project topics. That's fine, but just you need to remember that the focus of this subject is the multimedia. So if you give me a project that says, oh look, 5G is good to support multimedia and this is all the transmission features of it, that's not going to get you a good mark in this subject. But if you say 5G has these features, it means very low delay, and that's what it means for these multimedia services, then that's the sort of thing that would be of interest. Make sense? Okay. All right. Thanks, guys. Let's finish there. So,
Shortcut for the
Yeah. Lecture capture.
shortcut
In the LMS,
Oh.
there is no link for the lecture capture.
Oh, okay. All right. Thanks for that. I'll try to remember that to fix that over the next day or two, but don't give me a prompt. Thanks. I didn't realise I had to add that. I thought that would be there automatically.
这个过程我重新自己算了一遍，这个过程你懂吗？它就是不懂啊。它的意思就是，就是我们最后要表示的是这个东西，但是它这个地方说的就是 high probability 跟 low probability，那我们对应到这个情况的时候，就 A、B、C 这三个是 low 是 high probability，然后这个是 low probability， 就是很少有机会要我们需要这么长，就是要找到 A、B、A、C、A。我们有的时候，比如说这一个 pixel 它只要 A 嘛，那比如说可能另外 pixel 可能要 A、B、A、C 这样来表示，那有的 pixel， 那大部分 pixel 可能都是 A 或者 B 或者 C。所以说
ABC 到底是什么东西
？AB 就是 event 嘛，
事件是吗？
它好像就是。
The ratio between
ABC 就是组成那种组成这大的那个
事件嘛。
对， 对，对，
这事件比较少发生。
大概是这个意思。
嗯
然后
，low bound 是什么意思
low bound 就是我们如果要表示 a 的话，
嗯，
它这个是零到1，然后我们就用
中间开
这一块是0，这一块是1。
操，你用铅笔画的屏幕。
没事，它有平，所以这一块是0，这块是1。我们要表示这一块，我们最后表示是 a b a c a 嘛，所以我们要第一个先表示 a，那就是 a 就是取，这边是0，这边是1，那第一个我们要传输的就是0，表示这一块。然后我们把0这块，我们要找第二个字母嘛，就是 a b，a b， 那我们就把这一块放大到这边，这还是0，二分之一跑这
哦
在这。
OK。
然后我们要找 a b 这一块。那我这边写了呀，你看，我们那下面这个就是 a 嘛，a 的下面第一个还是 a， 那上面这一块，一个是 a b， 一个是 a c， 对吧？那我们还是这样，这边是0，上面这一块是1，那我们要找的是 a b 嘛，那 a b 是在上面这一块，所以我第二个传输的是 1a 嘛。懂我意思？他这里是跳了一步，他直接就跳到这一步了。
哎，我怎么感觉这个就是在，就是分，比如说我们最后得到这个，对吧？
对，
他
所以说我们如果要表示这种概率很小的东西，
就往下找，
我们就需要更多的 bits， 更多的这个。
等一下，它这里是 a b c， 那 a b c，
a 的概率是1/2，b 的概率是这么多。
那这个概率是谁规定的？一开始为什么 a 的概率会比其他两个多呢？这是谁规定的？还是他本来就这么规定的？
这个只是一个例子，就是在我们传输，在我们要 encode 一个东西的时候，我们不要管它是什么，只要
反正就是
能把这个例子搞清楚就可以了。
反正就是你这样讲我懂了呀。那这样讲，比如说我们找最后的 a b c， 然后 a b c 一开始就分布在就是这几个 a， 第一个 a， 然后就看这，然后 a 的话，然后第二个是 b 嘛，然后把 a 它自己这个放大，然后因为 b 在当中嘛，然后 a b 在这，然后再把这块截取出来，其实这个再放大，然后又分成3块 a b c， 然后就是a 嘛 ，a 呢就是这个提取出来，整个再分成 a b 放大，然后是 c 嘛 ，c 在上面，
是这样的，
然后把这个再放大，再放大 a b a 就下面，那就变成这个，
就是这个意思。
那就是一步一步往下套，
就是一步步往下，
就是
来找出我们要表示那个 code word 嘛，
就是
它
代码
到底是要多长？
代码
要多长嘛？所以说，如果有很多 a 的话 ，a 只要用一个0就可以表示了。只要我们看到，如果只要 input 是0，说明它就是代表 a 嘛。这个就是这个意思。
其实这个很简单，被他搞。
Arithmetic coding 它就是这个意思。我刚才是在算，因为它中间跳了一步。它这个
这哪里跳？
它这里 a 不能，就是它这里
a b a 嘛 a b 它这里直接到 b a b a 在这嘛，没跳啊。
不是，你看我们一步步分析的时候，第一个传输是0，没错，第一个传输那第二个传输是1嘛，1只能表示上面这一块啊，不能表示这个啊，你懂我意思吗？
让我想一下
1这边0跟1，因为我们只能表示0跟1嘛。
那这里已经没有1了呀，大哥，这里是2/1了，因为它是在下面这个部分。
对啊，我们要重新找呀，不是重新找，还是0表示下面这块，1表示上面这块。但是1这边包含了2段，你知道吗？只要有1，它都会包含2段。如果是0的话，就在这一段了。那2段，那我们还是那就是第二。
但是因为它 b 是在这个部位嘛，所以它就是在这个部位啊。
对啊，那所以 a b 它其实是在这一块的0，你知道吗？这个 a b 实际上是这一块的0。
对，可以这么理解。
所以说这一块的0，它中间少了一步，就是在这一步，我们要把这一块给拉出来。那这一块，这个是 a b， 对吧？那这一块是 a c， 没有 a a 了，懂我意思吗？
对啊。
所以说我们要表示 a b 的，要表示 a b 的话是010，因为在下面，刚好就是010，表 表示到 AB， 010才表示到 AB 啊。然后
老师不会考这个来计算吧？
我感觉我不知道，我在看往年卷有没有考这类题。
如果他比如说填几个空哈，比如空格这里应该是什么，这样可能还好一点。
他可能没有，他可能会叫你写最后他要输的代码，或者一个代码出的，他可能先给你这个，给你这个，叫你
往年考验看，
可能会这种。
回家再研究一下 ，OK， 讲的大概至少有个方向，知道什么思路。
但是它背后为什么这么做？它其实就是
它这些就是为了怎么样可以让那些图片啊、video 可以以这样的这种
传输的东西少嘛？
对 encoding 的方式来传输它。
对。
哇，这门课真的好
这
烦
其实有点难，
有点难。
而且后面包括 DCT 还有那些，如果
DCT 是什么东西我都不懂。
看那个的话，
我操！不是说这科不是说这科没有数学吗？啊，那我又被忽悠了他们。
数学很多，它后面还有什么小波变换什么的，我这东西我都忘了，好难。
那他们是怎么过的？
可能考试的时候让你简单一点，就叫你为什么要这样子，为什么要用这个，没说具体怎么算。
还有他那个就怎么说就，你可以分两部分考试，你知道考50句题格吗？你作业
不能考50呀。
你作业